I'm going to be talking about iterators today in OCaml. How many of you are familiar with OCaml? Oh, okay. That's a big chunk of you. That's really good. So as you know, OCaml is an impure, statically typed functional language. And OCaml's standard library doesn't include any built-in iterators. It only has lists, and lists are strict. So non-lazy, evaluated in-place lists. They can be infinite in some specific cases if it's like a self-repeating sequence or something, but otherwise they're like using up your memory. So usually when it comes to iterators, people use libraries, third-party libraries that implement some form of an abstraction model that maybe encodes like lazy lists or some form of sequences, generators, and I'm going to be talking about these things and I'm going to be explaining the differences between the fundamental models. And the interesting observation that I can make about the models that I'm about to present is that most of them are non-pure. They're mutable, they use exceptions, references, so not something that I would like to present like in a Haskell meetup, so to say. So I'm going to try to improve them, so bear with me. I'm going to try to take these models and bit by bit make them less impure, more pure, and at the same time I'm going to introduce some safety mechanisms and potentially even improve their performance. This talk includes a lot of code, so I'm going to be moving fast, ask questions if you don't understand something. I'm not expecting you to follow every single line of code. Just focus on the ideas and the models, I guess, and do ask questions, please. So this talk is not actually about iterators or anything. It's more about like fundamental ideas that we have in computer science, functional programming, OCaml or Haskell or whatever. It's about functions. And now that I'm thinking about this after the first talk by Ben, I'm thinking this talk is actually about folds again. So it's all folds. It's all just folds. And I'm hoping that you will see this pattern here. So this is a type in OCaml. And it says, I'm expecting a unit and I want something of type A. This is like a generic type for those of you who don't know OCaml. And what can we say about this? So in Haskell, of course, I think this function is like kind of impossible, right? Like you have to raise an exception or like use undefined or whatever. But in OCaml, you can specialize this function to integers, for example, and return like random integers because it's not pure. So you can, read stuff from the standard input and just throw the integers to the user. What I was saying is that if you specialize this function to integers, so like unit int, in that case you can produce integers. In Haskell you can produce one integer, but in OCaml you can produce multiple integers, so the whole domain of integers. And this function represents like the basic idea of the pool-based model. So you ask for something and you get something back. So let's assume that this function kind of produces values that we need. So it's like a very primitive form of iteration, so to say. How can we make it stop? Like, we need to give it a way to terminate its execution, signal that I'm done. How would you usually do this? So another way to terminate a function and say like, I'm done, I don't want to live in this world anymore, so just throw an exception. And by just using this primitive model, let's see what we can build that kind of resembles what iterators can be. So we have iter, and as you can see, the type is unit A. We define an exception, stop iteration. We have a global mutable reference. And then we have count as a function, and it dereferences the current value, checks if that element is greater than or equal to 3, and then rises an exception and increments the reference and returns that. So, okay, how do we use it? Well, we can call it. So you saw that the type is this, which means that we can essentially just call it, and we get 0, and then 1 and 2, and then once it's finished, it just, rises an exception. Okay, so this is brilliant, right? Like we have mutable state, exceptions. Notice that this if doesn't even have an else statement. So this is just, okay. But I promised that I would try to improve, this kind of models and iteration in OCaml in general. So let's see if we can do something better. Let's follow your advice and let's use options. And this is actually the type used by one of the very popular OCaml libraries called Gen that implements this kind of iterators. So pool-based iterators, give me something, I have nothing, iterators. Let's see how we can redefine the count function using this abstraction now. This looks better. We no longer have the global mutable reference, at least. So we don't have exceptions, which is even better. But we still have the local mutable state, right? So this function can be used by, well, first of all, initializing the iterator and then calling it a few times. And whenever it's done, it's just going to repeat none forever. And now that we know how to get the elements out of this pattern, let's implement something more functional, like a fold. So this is a fold. It takes an iterator. It requests for more elements. If the iterator is empty, then we just return the result. Otherwise, we continue the recursion, expecting the iterator to produce a new element next, because it has internal mutable state, right? This map definition, for example, uses local references. The only way that map has to communicate its termination is by checking if the inner iterator stopped. So this is why we have the stop flag here. Initially it's false, but then once the inner iterator is none, we say that stop is true. So we stop the map itself as well. Okay, so with this we can actually write some functional code. Underneath it's kind of mutable, ugly, OCaml, but this is, you probably know this kind of forward application operator. We have a nice functional interface. So why do we have to use this mutable state in most cases? Maybe not in map, but in other cases. And the type itself is just not flexible, right? Like this type, I mean, it kind of asks for mutable state. This is something used by Rust, I think. Python's iterators are very similar to this. You just keep asking for more and more iterator elements. You get the exception when the iterator is done. But anyway, we already improved this. But can we do better? I think so. But before we actually go into the improvements to this type, let me talk about something else. So what do you think is the opposite of this type? Maybe ignore the option here. Well, the opposite is like consuming elements instead of producing elements. And it might seem that it's like the opposite of iteration, but it's just a different type of iteration. And it's iteration that is based on the push model. So instead of requesting for elements, we supply a function that will get the elements as soon as the producer has them. Potentially all of them, which is really important. So this type is not flexible enough to implement actual iterators. But if we look at this one, I think this is good enough. And in this case, we have a function that takes another function as an argument. And this function here, the first argument, is a consumer. So it's like a callback. This thing here is a continuation specialized to the unit result type. Okay, so we take this callback function and expect the whole function to give us elements of type A, and then something will happen. So it's like a dev null, like a black hole for values, the consumer function. Now, let's do exactly the same thing and try to implement count with this. We have our type, so the iterator is something that takes a consumer and then returns unit. This is how we define count, the function that I showed you previously. For loops, you don't have those in Haskell. So as you can see, this function, this k argument here is the continuation function. So it's the consumer. And we iterate on the numbers from 0 to 2, including 2, and we just send them down to k. And k can do with them whatever it wants, you know. It's not the producer's responsibility to decide what has to be done. So now we initialize this counter, and we can call it. We just supply the function that matches the types, and it just works. Now, how can we get the elements out of this thing? Like, the type returns unit. Like, we are forced to use mutability again. So let's look at some functions, like filter, take, and fold. Can you not use references in this case? What about this one? Like, I think that the only way to extract something that is happening inside this consumer is to use a reference. So we initialize a reference to the accumulator. We run our computation, trusting our producer to give us elements. And then once that is done, we have the updated result, right? And take is a bit more complicated. I'm not going to talk about that, but yeah. OK, so what is this? Pull-based iterators and push-based iterators, like two completely opposite models to achieve mostly the same thing. So each one of them has their own advantages and limitations. The most common one is the ability to zip sequences. So for example, with push-based iterators, it's extremely hard to zip things because the producer is in charge and the producer decides when to send elements. So we'd have to wait for one of the producers to give you the second element to zip the pair of those forward. And I was thinking about this limitation, and I decided to implement something that would support this ability to zip. And of course, pull iterators support zipping because at any point of time, you can ask the two iterators to give you the next element. And once you have those, you can kind of yield the pair. Why did I want to do this? Well, because pull iterators are slow. The reason pull iterators are slow because they allocate an extra boxed value, optional value, for every single element that they produce. And that goes to the heap, and then the garbage collector is woken up, and it's complicated. While push-based iterators don't suffer from that problem. As you were saying, it's just function composition. So I decided to do this kind of small experiment and see if I could improve pull-based iterators using some techniques learned from the push-based iterators. And just for completeness, pull-based iterators are also called external iterators, and push-based iterators are sometimes also called internal iterators. So what is the kind of ideal model that I'm trying to achieve? And I think now that we've discussed these kind of trade-offs, this is a bit incomplete because, yeah, of course, I'm focusing on pull-based iterators, data structures, but in general, I wanted them to be pure. I'm not really sure why. Honestly, I think in OCaml, people usually don't ask these kind of questions. Like, if you have to use references, go ahead. Exceptions for control flow, why not? But I mean, this was just like an experiment, so and it kind of fits the Haskell meetup theme as well. I wanted good performance, safety, so closing file descriptors, for example, if needed, lazy on-demand initialization of those resources, early termination by consumers, and notification of termination by producers. You might know these two from pipes or conduits if you use them. And the interface that I implemented is similar to this one, so it's a very basic streaming model. The interesting bit is that take forces early termination, fold is the consumer, filter, well, doesn't pass all the elements to the consumers. So I mentioned that we were going to try to improve this type, so the pool-based iterators, and I decided to play with it. And the first thing that I tried was to introduce this explicit state. So lift the state to the type level and make it part of the declaration. We have the initial state there. So if we are iterating on a list, for example, that's the list that we have. Next is the function that expects the current list or the current state and produces an element from that list. and also the next version of the state, so that we can continuously get the elements out of the state. Or otherwise, it just stops saying none, and that means the producer is done. This is how we can implement count with this model. I think it looks nice. What do you think? It's pretty simple. So we define the next function that essentially expects an I for a counter, I guess. If it's and, then just return none. Otherwise, we yield the I itself and increment the state. And the initial state is 0. Okay, so now I also mentioned that we want to make this safe, so I decided to include these two helper functions, the init and free. Init protects the state from being unnecessarily initialized. So for example, if you create an iterator and then immediately say, like, take 0, well, the producer is not going to even open the state in the first place. And free, of course, just releases the state, closes the WebSocket, for example, or does some other additional work. This is how you implement fold with this. And I'm using the common in Haskell bracket pattern to make sure that whatever happens inside this loop is always properly initialized and cleaned. But otherwise, I think it's pretty straightforward. OK, so what is the problem with this? I was very happy about this. I mean, it's not massive improvement, but it's pure at least. It has better performance than original pool-based iterators, for the general case at least. What was happening here? Compared to the push-based iterators, this was still incredibly slow. So as I was researching some other ideas, I came up with this. I found this thing called scode encoding, and this is very similar to church encoding, which essentially allows you to represent a data structure as a set of functions, I guess. Functions that simulate the data structure instead of being the data structure, so it's focused on the behavior and not the structure. So the difference between scode encoding and church encoding, by the way, is that scode encoding uses the type itself, so it's self-references recursively. While in church encoding, I think lists are like fold rights, essentially. The reason I have this slide in Haskell is because if you search for scode encoding and OCaml, the only thing that you will find is like Haskell, essentially, all over the place. So, but of course, we can just translate this to OCaml. Sorry about that. OK, so this type has a function called view. The reason I'm using a struct, by the way, is because we need, or at least prefer, this R type, the result type of this whole thing, to be a universal type. And then this view function accepts two arguments, R for the nil case and cons for the non-nil case, I guess, for when you have the elements. And it's easier to understand with an example. So this is wrong, by the way. Should be 1. This is regular pattern matching on lists. You just check if the list is empty, 0 in that case, otherwise 1 plus recursively the length of the tail. With this view function, you do exactly the same thing, but you don't have to pattern match. You supply the value for the default case, the case in which the list is empty, and you supply a function that expects x being the element of the list, that one, and axis the type itself, so that one. You can't use axis on its own because it's, again, this kind of abstract, not abstract, but abstracted type. And you recursively call lang again in this cons function. So why should we care about this? Well, for me, the answer to this question was performance, essentially. So by using this functional abstraction, we avoid any runtime allocations on the heap and thus get better execution times. How can we use this type? Well, this is how you can construct nil and cons, and you can figure out the rest, I guess. You can, using these two functions, you can build up lists from any other data structure or source in general. So nil, for example, just ignores the f because it knows that it's empty. It's the definition of the empty list, and returns r. So we get 0 if we call that. Cons, on the other hand, ignores the r because it knows that it at least has one element, which is x, and then the continuation, the tail of the list is L here. So in that case, it's going to be 1, and so on. Now, I was looking at this, and I was really impressed. And I decided to merge the initial type that I had with this, and I came up with this type. OK, so let me explain step by step what it does, or what it is. Init and free are pretty much the same from the previous slides. Next is a bit different. So next is accepting the current or initial state, the current or initial result, and then it has this stepping function. And the role of the stepping function is to essentially take the next element from the state. It's given the next element from the state, and it's given the next state, and it produces the next result, which is the one that will be returned here. Now, the interesting bit is that this S has a similar role to the list that we have here. It only exists there to allow our stepping function to eventually call next again with a new R and with a new S. So it drives the recursion continues. OK, so now this is how our map looks in this model. So this is kind of identical to pattern matching or catamorphism, as you usually say in Haskell. So I'm destructing this state with the next, so the view or the uncons function, and I'm giving it the result that it has so far, and I'm expecting this step function to get an element, the next step, and then finally it calls the step from the inner iterator. So it essentially wraps this iterator here with a new next function and uses this step to continue, kind of let this step drive the recursion. This is take. Take needs to make some changes to the state. So not sure if you noticed, but in this case, I'm saying iter with next. So this in OCaml means take all the fields from iter record and replace next with next, this next. While in this case, I'm replacing all of them because I need to make changes, as I said. So init is actually the original state of the inner iterator, and then I also add the n counter, or limit, sorry. Free essentially ignores the counter and frees the state of our parent iterator. And then inside next, I have access to both this state from iter and I, which is the counter, and I can decide what to do next. The interesting bit is that since S is an existential type, I'm not actually allowed to use this type for my own purposes. The only thing that I can do is to essentially pass it to next, because next understands it. OK, so fold. And fold is the one who actually drives the recursion. So it's still a pool-based model. Fold is in charge. Fold is a consumer. And it has this go function, which is recursive. We use bracket to make sure that we handle the resources correctly. And then finally, inside our stepping function, so that's the one that's going to be used by map, filter, and so on, we call go again with a new state. So go is like the balancing thing between the state and the result. The state is like the bucket with some input, and the R is the bucket with some output. And go is kind of responsible for taking stuff from the S bucket and putting things through the F function to the result bucket. So I implemented this using this model, and I tried to make a simple benchmark that essentially used a few maps, a few filters, and a few takes, a very simple and primitive benchmark. It's not useful to judge any real-world production applications of this model, but at least it gives us some information. And here are the results. So the results are normalized, so this is showing the percentages between the different models. Here we have the absolute values. External is the original pull-based iterator. Internal is the original push-based iterator. External K is mine. Stream Fusion is the OCaml's implementation of something similar to Haskell Stream Fusion, I guess. The one that has yield, skip, and done that essentially removes the recursion from the combinators. And thunk list is just a lazy list, a list protected by a unit value. And I mean, it's performing well. I was really surprised. It's even better than our internal iterators. So, I mean, maybe that's an improvement. Maybe I just missed something, but I'm going to continue my research on this. So, yeah, this is it. And that's all I have to share with you today. Some conclusions before I finish. So, I think that in general, continuations or functions in general can lead to better performance. I've seen cases where, like, libraries that were mentioned here, like pipes or conduits, benefit a lot when converted to the continuation passing style. So it's something that we should always be aware of. Yes, it does complicate the code, but I mean, if you really need performance, maybe it's worth it. And also, I'm starting to think that maybe we just need a better syntax for our continuation-based computations that would make this problem just disappear. Pure programming is actually possible in OCaml. I mean, of course, it's not enforced by the type system or anything, but even in Haskell, you have to kind of pretend sometimes, right? Like all the unsafe functions and all of that. And also, impure functional code is possible in OCaml. Impure functional code is also possible. And it essentially means that, yes, the initial push-based and pull-based models that I showed you use mutable state and exceptions and all of that, but they are all protected by this interface. And like, I don't really care if take has to throw an exception inside to, limit the number of things to pass forward, because, OCaml's type system is really solid, so it allows me to build nice functional interfaces on top of ugly mutable code. So yeah. And finally, functions are the ultimate abstraction, in my opinion. Like, for me, it's really impressive how you can build really sophisticated things with just a few functions. And yeah, that's it.